All right, welcome to our first lecture for Chapter 11, IMFs, Intermolecular Forces, and then we're going to go ahead and combine solids and liquids in here as well. This first set of notes will be pretty short. I don't have a whole lot of time, but we'll see what we can get through. So we're going to talk about phase, and phase changes quite a bit in Chapter 11. Phase is a homogeneous part of a system in contact with other parts of the system, but separated from them by a well-defined boundary. So phases you're familiar with from physical science and Gen Chem are things like solid phase and liquid phase and gas phase. And so here we have a couple different phases of water where the glacier meets the sea. We have solid water, liquid water, solid water, liquid water, and they're all kind of mixed together, but you can definitely tell that this is the solid water and this is the liquid water. So those are two different phases of water. Solid phase we call ice, liquid phase we call water. And so this is some stuff that hopefully you're already pretty familiar with, but when we look at different states of matter like gases and liquids and solids, gases don't really have a defined volume. They're whatever volume the container they're in, that's the volume that they're going to be. Liquid, however, does have a definite volume. It doesn't matter if it's in a bottle or on a floor. If it's 20 milliliters a pop, it's 20 milliliters a pop. That's a definite volume. And then a solid has a definite volume and a definite shape. And so you could say, a marble has a volume of however many square centimeters, and then the shape, of course, is a sphere. And we're not really going to be able to change that unless we break it or something like that. So gas densities are very low. Liquid densities and solid densities are very high. And so generally gases are going to float on top of liquids or solids. You can compress a gas, and you cannot really compress a liquid very much, and you can't really compress a solid at all. So the molecules in a gas are very free to move around. Liquid, the molecules aren't quite as free as they are in a gas, but they can slide past one another. That's what allows us to pour a liquid. And then solids, molecules are vibrating, but they're fixed in one spot. So IMFs stands for intermolecular forces. These are attractive forces between molecules. What we've spent most of our time talking about so far is intramolecular. Intra is within. So within the molecule, intramolecular forces hold atoms together. That's stuff like a covalent bond, an ionic bond, that kind of stuff. And so we look at vaporizing water versus breaking bonds of water. To vaporize water, we're just trying to get liquid water to gaseous water. We're not actually breaking individual molecules apart. We're just going to pull one molecule away from all of his neighbors. It doesn't take that much energy. If you actually wanted to rip the water molecule apart and break the oxygen to hydrogen bonds, that's going to take a lot more energy to do that, because then you're doing an intramolecular force. You're trying to break this polar bond, this hydrogen bond. And with intermolecular forces, we're looking at just breaking one water away from another water. So they're generally a lot weaker. So there are some things we can do, and I hope to do, where we measure intermolecular forces. So how hard is it to pull a molecule away from its neighbor? Things like boiling points, melting points, the heat of vaporization, and the heat of fusion. Of course, if you're very strongly held to your neighbor, you'll have a very high boiling point. It's hard to take you away from your neighbor to turn you into a gas if you have really strong IMFs. If you have very weak IMFs, on the other hand, it's really not too terribly difficult to boil you, because it's easy to get you away from your neighbors. And so those are just some ways that we can get kind of some numbers to go with our IMFs. And of course, here's heat of sublimation. So generally, intermolecular forces, what we're going to be focusing on, are a lot weaker than intramolecular forces. Ionic bond, covalent bond, that kind of stuff. So let's look at some IMFs. Intermolecular forces, our first kind is going to be a dipole-dipole. A dipole-dipole force is going to be a polar molecule being attracted to another polar molecule. And so here's kind of the way it works. A polar molecule, we've talked about, has an uneven distribution of electrons. So it's going to have a positive side, and it's going to have a negative side. And the negative side on that molecule is going to be attracted to the positive side of the neighboring molecule. So it's a different molecule over here. And so what you get generally is the positives and negatives all line up, kind of like attracting magnets. And then the positives and negatives also line up here. They also line up here, so you can see that the positives are attracted to the nearest neighbors. And we're going to get a pretty strong IMF. Dipole-dipole is going to be pretty strong. So then there's what's called an ion dipole. remember an ion is a charged atom, so a negative or a positive atom, something along those lines, and it could be a cation or an anion, and here shows you two examples. Ion dipole, we've got an ion, the sodium cation, and then we have some molecule that's polar, whatever it needs to be. And the negative end of that polar molecule is going to be attracted to this positively charged sodium. And so we call that ion dipole. And it works the same way. If you have an anion instead, like iodine, then we would just be attracting really even the same molecule, the neighboring molecule perhaps. We'd be attracting the positive end of that molecule to the negative iodine instead. So that's called an ion dipole intermolecular force. And there's the positive, negative, positive, that's what's attracting. Okay, so when we look at water and cations, we use water to dissolve a lot of things, and water is great at dissolving salts and sugars and things like that. And one of the reasons is because water has the polarity of having these two positively charged hydrogens and then the negatively charged oxygen with its unbound valence electrons. And so it's able to attract both cations on the oxygen side and anions on the hydrogen sides. And so water is a pretty good solvent for that reason. Here we're looking at, because oxygen has those two unbound valence electrons, it's going to be attracted to a sodium, but it's going to be kind of a weak attraction. When we look at magnesium, the 2+, it's going to be a lot stronger attraction. This is more positive, this is more negative, so they're going to be a lot stronger attraction than a single positive. And so in solution, here's how water might be able to take apart one sodium from whatever the sodium is bonded to, chlorine or whatever else. All of those negatively charged oxygens on the water are all attracted to that positively charged cation. And so that's how we're going to get those things to dissolve in solution. So now we're going to get to dispersion forces. You might have heard them called LDFs, or London dispersion forces. Everything has LDFs. So if you're asked to list the types of IMFs in any chemical, anything, start with LDFs because they've all got them. And then move on to looking for others. So dispersion forces are attractive forces that arise as a result of temporary dipoles induced in atoms or molecules. What this basically means is that even nonpolar molecules are attracted to nonpolar molecules. And we ask, well, how can that be? If a nonpolar molecule has an even distribution of electrons, then how can it have a positive and negative side to be attracted to a positive or negative neighbor? And the answer is that while a nonpolar molecule does have an even distribution of electrons, those electrons are moving around really fast and pretty randomly. And just by random chance, all the electrons might get to one side of the molecule and create, just for a fraction of a second, a more negative side and a more positive side in that nonpolar molecule. And if that happens in their neighbor as well, they'll be attracted to each other. And these attractions only last for, half of a second, something like that. But when you figure there are billions and billions and billions and billions of molecules in, a jug of vegetable oil, the net result of billions of molecules all having these little tiny charges for fractions of a second is for the whole sample to have a force holding it all together, and that's the LDF. And so here's one where we get an ion and an induced dipole reaction. And so if we have something that is nonpolar, but we bring a cation near it, that cation is going to attract electrons to itself, and we can actually make a nonpolar molecule just a little bit polar for just a little while, and we can get a force that way to hold these things together. And then here's a dipole-induced dipole. And so the dipole is we're bringing in a polar molecule. We have a non-polar molecule, but when that polar molecule comes in, the positively charged end is going to attract a few electrons, and we're going to actually make that non-polar molecule just a little bit polar for a little while. And so LDFs aren't a very strong attraction. Really, they're going to pretty much be our weakest IMF, but they're strong enough to get the job done. And so if you have induced dipoles interacting with each other, like if this is our LDF example, and this little guy just happens to have electrons vibrating a little more on the right side than the left, then he's going to bring the more positive side of his neighbor to him, which will leave a negative side, which attracts a positive side of his neighbor. And when you look at these different little snapshots, none of them are particularly organized in any particular way. And they're all going to change here in like a fraction of a second, but overall, they'll hold a substance together. So that's dispersion forces. Polarizability. To be polarizable is the ease with which the electron distribution in the atom can be distorted. So how easy is it to make something that's not polar, polar? Polarizability is going to increase with a greater number of electrons. A more diffuse electron cloud basically means bigger. And so you look at the number of electrons here, and you look at how our melting point changes as we go down this group. And basically what we're doing is we're adding electrons, adding more electrons, more electrons, more electrons, more electrons. And so going down, we get more and more and more electrons. So we're increasing the polarizability of Ci4 compared to CH4. Even though they're both technically nonpolar, this one is going to have a lot higher melting point because of all of its electrons. So it's going to have to be more easily polarizable, and it's going to have a stronger London dispersion force as a result. And so it's a little harder to melt it because they're so strongly attracted to each other. And that sort of makes sense if you think about, these quickly moving electrons being the result of, or rather causing, these quickly moving electrons causing these temporary dipoles. If you have more quickly moving electrons, then you're probably going to have more of a chance of getting temporary dipoles. Whereas if you just have 4 on hydrogen, there's only a few there. They're going to pretty much cancel each other out. But if we get a bunch like on iodine and carbon, then we've got a lot better chance of getting that temporary dipole. And so here's the increasing strength and the increasing melting point that we see as a result of that. So another way to tell dispersion force strength, if you're asked to do so in a question, is it generally increases with molar mass. And so you could look at this and say, what's CH4 weigh, what's CF4 weigh, what's CCl4 weigh, and get their grams per moles. And if you have to guess, go with the heaviest and say the heaviest is going to have the strongest dispersion forces. So that's all the time we have for today. I hope you found this helpful, and I'll see you next time for video 2 for chapter 11. Thanks.